Hey, this is Leach with Simpson Math, and in this video, we're going to be talking all about domain. We'll start off with getting our feet wet with talking about domain and range with piecewise functions, and then ultimately we'll be talking about functions that have their domain restricted, and how we can determine the domain of those without even needing to graph them. So let's get started with this piecewise function that's right in front of us. What I want you to do is to try to determine the domain and the range of this function. Just a reminder about a few notation things. These closed dots mean that the function exists on that number. But these open circles, these open dots, mean that the function exists almost on those numbers. If you could get as close as you could to that number without touching it, playing the I'm not touching game like a little nephew or something, then that's what these open dots are. And then just for clarity, each of these dots are on nice, pretty intersections of nice integers. So see if you can determine the domain and the range. I'll be doing it in both interval and set notation. So give yourself a second and see if you can figure that out. All right, so let's look at the domain first. So for my domain, I'm going to go as far left as I can, and often I like to think about things in interval notation, so let's see if I can do that. So I'm going to go as far left as I can, and there's nothing over here, so as far left as I can go is this -3. Now, again, when I think about domain and range, I think about smashing everything onto the corresponding axis, like it's a big industrial press or bookends. So if I'm talking about domain, everything's going to smash down onto this x-axis. So if I was to smash everything onto the x-axis, this open circle dot is talking about that -3. Now, we're not going to be able to quite get to that -3, so our domain is going to be start with a parenthesis and -3, because we can't quite get there. All right, so then if I'm at this -3, almost, I can work my way to the right, to the right, to the right. This solid dot, that's fine. It doesn't interfere. Keep going, keep going, keep going. And then, oops, when I get to this 2, there's literally a hole that I just have to hop over. So in terms of interval notation, I have to go from -3 to 2 and then stop my interval. Now I have a parenthesis because I'm not going to be able to touch it. It's literally, again, playing that I'm not touching game. But then I need a little piece of glue to be able to glue all this together with my next piece, and that's the U. Ooh, that's really ugly. The U for union. So nice big fat U. It's just a piece of glue to say I have this interval, and I want to attach on this other interval and stick them together with glue. So picking up, hop over the 2, starting on the other side. I go from 2 all the way over to 5. And I am touching that 5. That is a square bracket. I am touching that 5, almost touching the 2, but I am on the 5. So I'm going to go from almost 2 to 5 square bracket. And this is in interval notation. I'm not worrying about labeling at this point. I'm assuming that you know the difference in interval and set notation based upon our previous videos. All right, so what would it be for the set notation? And I'm going to do the set notation in orange. So it would be the set of all x's. So I open with my set notation bracket or brace. So it's a set of x's such that. And so there's a few ways we could do this. We could make 2 different statements, but to me, I want to do what's the most efficient. So I'm just going to make one statement. So overall, I see that I can go from this -3 or almost -3 all the way over to 5, and then just go, well, it's not at 2 because it's just there's one little number that I can just pluck out. So I could say that this is from -3 is less than x, which is less than or equal to 5. That's very similar to sort of that idea of -3 with that parentheses, comma, 5 square bracket. So that's that idea. If that hole wasn't there at 2, this is how I would write that. So notice we have a less than because it's not touching the -3, but a square bracket because it is touching the 5. And then say, oh, but, so put a comma that's really aggressive comma, and x does not equal 2. I'm going to, in a second, spell out how you can think about this when we talk about range, but that's how that compound inequality works. Another way to do this, I'm just going to lightly write that this domain here as well. I could have said it's a set of x's such that, and just like we did with the integral notation, make two inequalities. -3 is less than x, which is less than 2, comma, 2 is less than x, which is less than or equal to 5. So you can do that similar idea that we did with the interval notation and just break it apart. This would especially be useful if, instead of it just being a whole like that, if I had a piece of a function here, and then we had this piece with a large break in the middle, then you'd want to just separate them with a comma like that and have two separate inequalities. All right, let's talk about range. All right, so with range, how far down can I go? Well, I can go all the way down to almost 4. So again, I'm going to bookend this, just smash it onto the y-axis. So this value gets almost to that -4, but not quite. So I can say from almost -4 to, all right, so I'm almost at -4. You can even kind of imagine a parenthesis right there. Journeying all my way up, on my way up. All right, so what's happening with this -2? Is there, if I was to list all points on this function, every single dot that you could imagine along this function, there's an infinite number of them. But if you were able to list them all, would you list a point? Is there an ordered pair somewhere that has a y value of -2? Yeah, I do right here. Even though there's an open circle here, when I smash and bookend this onto my y-axis, I'm going to have this open dot essentially right here, or you can think it's almost touching here. But this open dot here gets filled in when this gets smashed. So we're going to go from -4 all the way up to being on and touching 6. All right, so this open circle dot gets filled in by whatever points right here when they kind of smash onto the y-axis. So it goes all the way from -4, almost -4, all the way up to 6, square bracket on that 6. Now for set notation, it's the set of y's such that, and we're going to do that same thing, -4 is less than y is less than or equal to 6, close my set bracket. Now let me explain this inequality here. So just as a clarity, just as an explanation about this y, what we're doing is this is called a compound inequality. So I'm saying y is greater than -4. All right, so over here, do you agree that I have y values that are greater than -4? Yep. But it doesn't go all the way up, so we're going to use the word and. So both statements have to be true. And y is less than or equal to 6. So over here, is it true that I have y's that are less than or equal to 6? Yep. So with these two statements, I'm saying y has to be bigger than -4, but not touching it, and less than 5. I'm only going to be dealing with those that are in the intersection of those two spaces. And that's what this and says. So what I've drawn here, and this is how I really want you to do this. I don't want you to use two separate ones with an and, though these are both true. These are equal statements. What we've done is we've basically picked this up. Imagine me picking it up, flipping it over, and sticking this y on top of that same y. So if I could pick this up, flip it over, and stick it on that y, we end up with -4 is this flips less than this y, and then our y is less than 6. So it's called a compound inequality. You can basically think it's very similar to this interval notation. We're just saying this y is in between these two values on this 6, but not on that -4. All right, so that's how we write in set notation. I think this is probably the first time you're seeing the compound inequalities, so I wanted to give you a chance to do that, to see that. All right, so just a quick little what if. What if instead of it being a dot here, so it's the same thing that we had up there, all I've done is I've just changed this to being an arrow, so it's just going to go off in that direction that that arrow is heading, so forever and ever and ever. What will change? So take what we just did, and I want you to rewrite this with this new change for the arrow? How will the domain and range change? So take a second, pause the video, and try that one on your own. All right, so let's do this. So our domain is going to go from negative infinity, sorry, woo, lies, going to go from this -3, again, that hasn't changed, so almost that -3, and then going to have to hop over that 2, just like before, but this time it's not going to stop at the 5, so it's going to go on forever. So I'm just going to basically copy down what we saw up ahead at the top of the page, so -3 to 2, union 2 to, but instead of stopping at 5, it's going to go to infinity. So infinity, close parentheses. In terms of the set, it's basically the same thing, but instead of it stopping at that, I don't have to use a compound inequality. You could, and I've seen it is proper. It's okay to say less than or equal to infinity. That's cool, but to me, that's just unnecessary writing. It's going to be much more efficient to just say this is the set of x's such that x is greater than -3. So we're saying x is greater than -3, which is taking me from this -3 almost forever and ever and ever to the right, but just not at 2. So a comma, but x does not equal 2. All right, that's how I would like you to write that domain in set notation. And then what about the range? So for our range, we're going to start at almost -4. Instead of stopping at 6, we'll go all the way up to infinity. So that's going to be -4 to 6, square bracket, oop, lies, I was copying the wrong thing, -4 to infinity, right, because we're not stopping at the 6, and again, it's a parentheses around the infinity because we can never touch infinity. In terms of set notation, it would be the set of y's such that y is greater than -4, and that's that. All right, so that's that slight tweak that if we remove that dot and we made it be an arrow. So you'll find there's lots of practice that we're going to have over this set where I give you a picture and you need to then tell me what's happening. And so remember these skills and both of these different ways of writing it. All right, so let's take a look at this one. Here, it's quite the opposite. I'm saying, here's this problem. I'm saying that there's going to be a function that has this domain and this range. I want you to draw a function. Now there's technically an infinite number of possibilities that would satisfy this. So there's lots of things. Big key things that students mess up, they don't draw a function, all right? So that means make sure that you don't have any repeated y's, or they'll mess up on some of the endpoints, or even put some values where they shouldn't. So kind of like a little puzzle, take a second, pause the video, and try this on your own. All right, so let's take a look at doing this. All right, so for me, what I like to do when I start this is I will make just a note to myself over on the margins of the graph and not in the graph itself. So when I'm thinking about the domain, I'm going to sort of kind of move my x-axis here mentally, just kind of like on the edge marginally for just a second and make myself a note. So I'm using a light blue. Is that visible? Let me make it thicker. Yep, you should see that. So I'm using this light blue, and I'm going to basically make a graph over here on the side as if I'm making it directly on the x-axis, but just way over on the margin. So it's going to go from -2, where there's a closed dot, all the way over to 5, where there's an open dot, and drawing a line. So I'm kind of extending this down. If I zoom in, the grid gets a little bit bigger. So I'm going from -2 to almost 5. I'm just making that note over here to the side so it doesn't get in the way, and I'm making it really lightly. So light I might erase it at the end. All right, so whenever I make my graph, I have to make it so there's a closed dot and an open dot, and they can connect. I can do closed dot, open dot, and do something like that. That's fine, whatever. Notice there's an infinite amount of possibilities here, but I cannot put anything over here or over here. All right, so let's do the -3 to -1. So I'm going to take my y-axis and sort of kind of make a little note to myself over here on the side. So if I have an open circle at the -3, and then an open circle at the -1, and then I have things in between it. Okay? But then there's nothing between -1 and 1, but I am touching the 1 right here, and I have graph at 3. It is touching at 3 and everywhere in between. So now I know I have to go all the way over to this edge. I have to go all the way over to this edge almost, and I have to fill in between. I also have to fill in between up here, but nothing can go in between those spaces. Okay, so let's do this. Like I said, there's lots of ways that you could end up doing this. This is just one of the ways. So I noticed that I have an closed dot, and a closed dot, and I'm just going to make those intersect right there. Just make my life easy. I could put this in lots of other places, but might as well go ahead and make my closed dot right there. So that agrees, okay. Now, so I know that I'm going to have two separate chunks. I have to have a chunk up here and a chunk down here, and they cannot be on top of each other. So I cannot do this because that is not a function. I cannot do this because that's also not a function, just even, but less egregious, right? So I know at some point I need to, up here on the top, I need to travel from the top down. I cannot draw a vertical line because that would also not be a function. So let me just move over a little bit and put a closed dot and connect the two. So that just satisfied that top section. And that satisfied from here all the way over to that 1 or so. Again, you could have put it in any other number of things. You could curve it. You could, no, not like that. You could curve it like this. That would work. Sure. Like I said, infinite possibilities. Over here on the other side, I have to have open circles now when I do this. And with these open circles, notice it's a continuous flow. So that means that wherever I pick back up, I'm going to have to pick back up with an open circle right under the 1, so that way those like fill in on top of each other. I could put this in a few places, but I'll go ahead and put this at the bottom at -3 with an open circle. You could just as easily put it at the -1. And then I'm going to go over to the 5 with an open circle and fill in here. And then I'm going to do a quick double check before I move on. So I'm starting at -2, so I should be -2 all the way over to almost 5. So I'm at -2, yep. I have values. This, I have a value at 1, but as soon as I move to the right, it then jumps down here. So I have values all the way to almost 5. So my domain is good. For my range, from -3, almost, all the way up to -1, almost, and then nothing, empty space. And then 1 on it, and then all the way up to 5, all the way up to 3, and I'm on it. All right, so there we go. So that's how, given a set of domain and ranges, I can draw a function. Make sure it's a function. It passes the vertical line test. I have a dot over itself, but this is a closed dot. This is an open dot. There would be a problem if this was also closed because it would fail the vertical line test right there. So make sure it's a function. And again, lots of possibilities. This is just one of them. All right, so let's move on. So we are going to now be talking about our functions with restricted domains. So we have 2 parent functions with the restricted domains. We have 7 parent functions we've talked about so far. We've talked about the linear. That domain is -infinity to infinity. Then we talked about the quadratic. That's -infinity to infinity for its domain. Then after the quadratic, we talked about the square root, which the square root starts like this and takes off. And we remember that we cannot plug in square roots of negative numbers because those aren't real, and when we're graphing real things. So the square root has a restricted domain. So I'm going to define, let's make it less thick. I'm going to say that this is f of x is the square root of x is one of our restricted domains. And what's special about it? Well, our domain is from 0 to infinity, or the set of x's such that x is greater than or equal to 0. So the gist of this is that our x's have to be positive or 0. They're not allowed to be negative. Let me switch my colors. All right, so I'm going to make a statement that says x is allowed to be positive or 0. And I wrote that in green. And then in red, I'm saying x is not allowed to be negative. Now, which of those two statements is kind of easier to communicate? Is it easier to say x can be greater than or equal to 0, or x can't be negatives? Which one of those is easier to say using an inequality statement? Well, in my opinion, I like to say, in this particular case, it's easier just to define that x has to be positive or 0. So I'm going to say that that is x is greater than or equal to 0. So with x being greater than or equal to 0, that is something definitive I can say. You can say x is not allowed to be negative, and so that would be x less than 0, and you put a slash through it. That's a weird symbol for most of us, so that's why I'm not using that. So we're saying x has to be greater than or equal to 0. And notice in our domains, we often are, that's the wrong thing to highlight. In our domains, we're saying where x is, not where x is not, because we're having to still list those things. We often will say that. So x is greater than 0, so we're keep that in mind. All right, so we talked about square roots. Then we talked about cubes, x cubed. Those are fine. Those are all real numbers, negative infinity to infinity. Then we talked about cube roots. Those domain is negative infinity to infinity. Then we talked about absolute value function, that v. That's negative infinity to positive infinity. Then our seventh parent function that we've talked about so far is the rational parent function. That's 1 over x. And as we remind ourselves that x cannot, that in that case, x cannot be 0. The denominator cannot be 0. So if I have, and I'll just saying f of x again, but so if I have a function, f of x, and it's the rational function 1 over x, the domain in terms of inequalities, that would be negative infinity to 0, union 0 to infinity, with parentheses around both of those zeros, because we're not touching 0. Whereas the set notation is x such that x can't be 0. Now, there is an implied, it's like full name would be to say that x is an element of the real number set, so we're saying where x is, and then we exclude, we're saying, oh, but x is not 0. Now, we often don't have to worry about the x is an element of the real number set because that's an understood statement. So we are saying where x is, and then just removing that one part. That's the most efficient, because otherwise I would have to say x is less than 0, oh, and also x is greater than 0. So this is much more efficient. So to me, again, I could say positively x is less than 0 and x is greater than 0, but it's much more efficient to speak negatively in this case, to say x cannot be 0, or just to say x is not 0. All right, so let's keep these two statements in mind. X for square roots, x is, or what's in this case, what's under the square root. What's right here under the square root has to be greater than or equal to 0. And here, what's in the denominator cannot be 0. Just a reminder about that. This is a good spot for that. Remember, if I have some number, if I have 0 divided by some number, let's call it k, that is okay. That is just 0. But if I have some number n, let's call it n, and we divide it by 0, that's a no-no. 0 on the bottom, that's a no-no. That is undefined, and that's why we have that domain restriction. So keep that mnemonic handy. All right, so let's take a look at this example. Let's write the domain of this function. So we have f of x is x squared plus x minus 12. So what's the domain of this? Well, this is a quadratic. As we've talked about with our parent function with quadratics, unless we're like in physics class or we're doing a story problem and we're talking about physical restrictions about something, like if I kick a football and this is time and height, and we don't look at negative time, and then the ball doesn't go through the ground, and so we have restrictions. Unless we're dealing with that, and we're not, we're just dealing with the graph itself, then it's all real numbers. So in terms of interval notation, it's negative infinity to infinity. Then in set notation, that's a gross set bracket, that's better, x such that x is an element of the real number set. So there's our interval and our set notation. All right, cool. So now, so not everything is going to have a domain restriction. We're going to have lots in this. I put that example there just to remind you that not everything has domain restrictions, just when we see one of our two functions, the rational or the square root. All right, so let's take a look at this g of x. So g of x equals 2 over x plus 5. Now, is there a problem? Is there something that x is not allowed to be here? Yeah, so hopefully you're like, oh, well, x can't be something with this denominator. What's happening with this is, for me, whenever I think about domain restrictions, I think about Star Trek and Red Alert. So whenever, if you've ever watched Star Trek, the movies, the TV shows, when something happens, something's gone wrong, the captain just says, "All right, Red Alert," and all the colored lights everywhere just turn red from the bridge, to the hallways, to the lower decks, everywhere. Just basically all lights just turn red. So oh crap, it's about to go down. Is this business as usual, or is this red alert? Well, this is definitely a big old red alert. So why is this a red alert? Well, because I need to change colors on my with my highlighter. Need some reds. Why is it red alert? Because of that x plus 5 in the denominator. All right. So let me add a little bit just clarity. I know we just wrote this down, but let me add in. So if we see a rational function, what we have to determine is we have to set the denominator to be not equal to 0 and solve. And I have that note right above my head. If it's a rational function, you just make the denominator be not equal to 0 and then solve. So in this case, what is our denominator? Well, it's x plus 5. I'm going to set it to be not equal to 0 and then solve. So, well, x is, and I'm going to add 5 to both sides, x cannot equal -5. So if I plug in -5, I get -5 plus 5, which is 0, and we end up with 2 over 0, and that is undefined. That's a big old problem. This does not work. So that tells me everything I need to know about the domain. X can be any other number, just not -5. So imagine I have a number line. There's 0. There's -5. I have a big old open dot, make that thicker, open dot at -5, and everything else is fine. All right? So what would be our domain here? Well, our domain, and at this point, we're just talking about domain. I know we talked about range at the beginning, but here on out, we're only looking at domain. So in terms of the interval notation, the domain is from negative infinity. Woo. So we're going all the way from negative infinity, trucking on up until we get almost to -5. We can't equal -5. The moment it equals -5, it's undefined. I'm going to draw that U for union. It's just a little piece of glue that glues it to the second part. We hop over that -5 to the other side, and we say -5 to infinity. All right, then for our set notation, we say it's the set of x's such that x does not equal -5. There's an implied right here. X is an element of the real number set, so we're saying x is all real numbers, just not -5. But like I said, we don't have to keep writing that because we're dealing with real numbers right now. So we have a general understood level of that communication. All right, so when you see an x in the denominator and you have to determine the domain, we go into red alert. And so when you see a red alert, we have to then determine what level of red alert it is or what kind is it, who's attacking us. In this case, it's the Klingons, and they have have a cloaked bird of prey off our starboard bow, and we have to deal with this. We have to figure out the right code to decloak their ship so we can attack them or evade them or whatever. So we have to determine that right sequence and then solve. So let's look at this one. H of x is 2x over x squared plus x minus 12. Make sure that your fraction bars are long enough. They need to extend to the left past your furthest left object and to the right past your furthest right object. Mine barely does, so I can make it a little bit longer, I guess. But it's a good idea to make sure that they are nice and long. All right. So is this business as usual, or is this red alert? Business as usual or red alert? Well, we had that 2x. This 2x is in the numerator. Is that a problem? Nope, that's fine. That's a friendly Vulcan ship just flying by. We're good with them. Oh, what about this? This x squared plus x minus 12 in the denominator is a big old freaking red alert. That's a problem. That's the Klingons. They're attacking us. They're cloaked. We have to figure out what's going on. So that means, what do? Well, that means that since it's a rational function, we're going to set the denominator to be not equal to 0 and then solve. So let's do that. So I'm going to set x squared plus x minus 12 to be not equal to 0 and then solve. Good thing we've had that factoring review. So we need to solve this by factoring. So I'm going to do the AC method. So AC is negative 12. A is 1. A is 1. C is negative 12. What multiplies to be negative 12 and adds to be 1? I hear someone out there say negative 3, positive 4. Yes, that's right. Negative 3, positive 4. Negative 3 times 4 is negative 12, but if I add them, I get a positive 1. Now, are we allowed to just jump? Can we just jump straight to our factors, or do we have to do all 4 steps? Have those middle 2 steps? Yes, we can jump because our A is 1. So let's jump. So we get x minus 3 times x plus 4, where these are just our factors that we had a second ago. Still keep that not equal to 0. You got to keep that. This is an equation that we're solving. So just like the 0 product property, it also works for the not equal to statement. So I'm going to set each of these to be not equal to 0. It does not work with any other number, only with the zeros. But even though this fancy term equivalence relation has changed, we can still use a 0 product property. So then solve each of them. Make sure to keep slashing that equal sign every time. So we're saying x is not allowed to be 3, and x is not allowed to be negative 4. Let's just test that. So if I plug in 3 right there, that's a 3 squared, which is 9, plus 3 minus 12. Yep, 9 plus 3 is 12 minus 12. That's 0. That's a 0 in the denominator. Big old problem. That's an issue. All right, what about negative 4? Negative 4 squared is 16 minus 4, when I just plug in the negative 4 by itself, and then minus 12. Well, negative 4 minus 12 is negative 16. 16 plus 16 is, 16 minus 16 is 0. That's another divide by 0. Big old problem. So, again, it might be helpful to draw a little sketch of a number line. So here's 0, there's 3, here's negative 4. So we're good with all of their numbers, just not negative 4 and 3. So I'm good with all of these numbers, all of these numbers, all of these numbers, just not negative 4 and 3. So let's do our domain and range. Sorry, lies, just domain. So interval notation, negative infinity to negative 4. Parentheses around the negative 4 because we are not touching it at the moment we touch it, it becomes undefined. Negative infinity to negative 4, union, negative 4 to 3. Another union, 3 to infinity. So this is the first time we've seen a double union. If you just think about those U's as just a little piece of glue, a little dot of glue. If you've been to the craft store and you've seen the little glue dots, they're fun. They're like stickers, but they're glue. So they're just little dots of glue. So I have this piece right here, negative infinity to negative 4. Then I have this piece. Oops, a little bit bigger. -4 to 3, right? I just need to glue it on to that first one. And then I have this last one, 3 to infinity. Pick that up, put my glue dot on, stick it on, so I can glue them together, those unions. Now, let's go and do set notation. Then I'll do my ponderance. All right, so set x such that, the set of x is such that, implied all real numbers, but just not where. So x just does not equal, and I like to write them in order, -4 and 3. So there we go. So that's set notation. My ponderance is, what about 0? My little note. What about x equals 0? What happens if I plug 0 in? So I get 2 times 0 over 0 squared plus 0 minus 12. Well, in the denominator, 0 squared plus 0 is 0 minus 12. I get -12 in the denominator. In the numerator, I get, gasp, 0. Is a 0 in the numerator okay? Do I need to go back and change my domain? No, of course not. This 0 in the numerator, that's just 0. 0 is fine. 0 is a number. Don't discriminate against 0. It is a number, just like 1, just like -1, just like a half, just like every other number. It is fine. It is not a problem. It's just 0. All right? So I can plug in 0 and I get a value. If I was to graph this, I plug in, when I plug in 0, out comes 0. So that just tells me that this graph goes through the origin. Just happens to. That's okay. All right? So don't stress about the numerator being 0, and don't stress about plugging in 0. That is okay. So x plus 0 in this case is okay. Literally, based upon my mnemonic, that is 0 over k. That is okay. That's just 0. All right. Let's move on and take a look at this one. So j of x is equal to 1 over x plus 8 plus 3 over x minus 10. So, red alert or business as usual? You might have seen me erase these a second ago because I forgot to get rid of them. So we do have red alert. We have 2 Klingons attacking us, one off our starboard and one off our port. They are surrounding us. Our sensors are picking them up, but we don't know them. We can't see them because they're cloaked. We have to figure out their unusual cloaking signatures so we can decloak them and engage with them. So now, what did I say? What is the problem with the red alert here? It's that the denominator cannot be 0. So what do I do with this? Well, I take take this x plus 8. The x plus 8 cannot be 0. What else? Well, also, the x minus 10 cannot be 0. So let's solve them both. So, well, x cannot be -8, and also x cannot be positive 10. So x can't be -8, and x can't be 10. They both have to agree. They don't conflict with each other. They just are both not things that aren't allowed, just like before. Technically, there's an or on all of these, a little implied or. So we end up with interval is x plus, copying the wrong thing. Interval is from -infinity to -8. Union, -8 to 10. Make sure your infinities and your 8s don't get turned and be confused, like I just drew a -infinity instead of an 8. Union, 10 to infinity. And then set notation. Set of x is such that, again, we've implied all real numbers, but I'm just going to say x does not equal -8 and 10, and I prefer it if you write those in numeric order from least to greatest. All right, so that's the domain restrictions for this one. All right, let's take a look at k of x. So, what the Mr. Leach, you're just acting a fool now with all this fractions inside of fraction business. Yep, you're right, I am. All right, so obviously there's some red alert business going on, but first, how many ships are out there? How many alerts are happening? How many things are going on? What is happening? Well, for one, do you agree that that light red that I just highlighted, I'll do it again just a little bit clearer, that's a denominator, and 0 cannot equal that. Is there another denominator? There's another denominator inside the denominator, so both of those things are not allowed to be 0. So this means that, one, we have 3 over x minus 2. All of that is not allowed to be 0. Additionally, x, just by itself, is not allowed to be 0. Both of these statements are true. These are both denominators in this problem. They are not both allowed to be zeros. So let's solve. So I can add the 2 to both sides. Come on now. 3 over x, add the 2 to both sides. So 3 over x does not equal 2. I can now multiply both sides by x. These x's reduced to 1, and I now have 3 does not equal 2x. And then I can divide both sides by 2. So we get 3 halves does not equal x. And when I solve this one over here, well, lucky me, it's already solved for x. X is all by itself. So in terms of set notation, let's do interval first. In terms of interval notation, we're going to go from negative infinity all the way up to, which one do we get to first numerically, 0 or 3 halves? Well, the 0, because it's 0 and 3 halves is positive. Union, 0 to 3 halves. Union, that's a gross looking U. We'll try that again. Union, 3 halves to infinity. See why it's important to be least to greatest? And then set notation, the set of x's, such that x does not equal 0 to 3 halves. Sorry, 0 and 3 halves. 0 or 3 halves. Technically it's an or. Alrighty, so that's that one. Alright, switching gears. Now we have this p of x. So p of x is the square root of x plus 2. Is this red alert or business as usual? Now, this is going to be a red alert, but is it the Klingons attacking us? Is it the fact that this is in a denominator? No, silly. It's the Romulans this time. The Romulans are attacking us. So that's a problem. So with these, what's different about this is in a square root. Let me just rephrase what we did at the beginning of this lecture. So if we see square roots, I said earlier x had to be greater than or equal to 0, but that's when the x was what's underneath the square root. Quick little vocab term. Let me say square root of, let's just say k. But in this case, k is a vocab term called a radicand. A radicand, which is a technical term for the thing under the radical. Just like when you do the divisions, and there's addend and dividends and all these and-ins, that's those similar words. So you set the radicand to be greater than or equal to 0, and that's also right above my head. And so again, what is a radicand? Just everything under the square root. Now this is just for square root. So among our 7 parent functions, there's 2 things that are radicals that have a radical in it or a root: the square root and the cube root. Cube root's fine. I can plug in negative numbers all day long. I cannot with the cube roots, or I can take the cube root of negative numbers. I cannot take the the square root of a negative. So, in this case, I'm going to take this radicand, which the radicand is x plus 2. I am not squaring both sides or anything like that. This is just a logical step to pull out the radicand and say it has to be greater than or equal to 0. Just like in these steps, this was just a logical step to say, I'm going to take the denominator and set it to be not equal to 0. I'm going to take that denominator, set it to be not equal to 0. It's a logical step, not doing an algebraic manipulation to get it by itself. All right, so now I have x plus 2 is greater than or equal to 0. So what is x? Well, x has to be greater than or equal to negative 2. Subtract the 2 to the other side. So this is the range. I don't have to finagle with it. So it's, again, with real numbers, but when x is greater than or equal to negative 2. So you need a number line that might be helpful. Here is 0. Here is negative 2. In this case, we are on and touching negative 2, and then it's all numbers bigger than it. If I plug in a number smaller than negative 2, nope, doesn't work. Negative 2, that's fine. Plug in negative 2 plus 2. Well, what's negative 2 plus 2? That's 0. What is the square root of 0? That's 0. I can take the square root of 0. It's just 0. 0 times 0 is 0. So we're fine with that. But if I plug in anything smaller than a negative 2, negative 2.1 plus 2 will end up being the square root of negative 0.01. That is imaginary. That's not the imaginary number, but that is not real. All right. So the moment it is teeniest tiny smaller than negative 2, nope. Negative 2 itself, cool. That's 0. Bigger numbers. All right. Interval notation. Interval notation. Negative 2 to infinity. Set notation. X such that x is greater than or equal to negative 2. You can also take advantage of the fact that you've hopefully now have mastered graphing using transformations. So this particular function is just a square root function that's gone left 2, 1, 2, square root like that. So if you understand your transformations, that can also help you make sense of our domain. Additionally, you can always just take this, or in this case, take this whole thing, plug it into Desmos, and check those values. You can click on those points and move around, and when you get to 0, it'll say 0, undefined. When you get to 3/2, it'll say 3/2, undefined. So take advantage of that, and it will pop it to be an open circle. So I think that's kind of cool. Most graphing programs won't do that. All right, so Q of X. So is this business as usual or red alert? Red alert. Yep. Why though? Because it's the Romulans. It's the square roots, of course, right? So what is the problem? What's the fix for this? I have to determine what is permissible or not. In this case, it's easier to say what is allowed. So I can say 5 minus 7x has to be greater than or equal to 0. So whatever comes out of that it can be 0, but it has to be 0 or bigger, right? Cannot be negative. Cannot be less than that. Notice with this previous one, negative numbers were fine. I can plug in negative 2, negative 1, negative 1.5, negative 0.1. Negative numbers could go in here, but once it's simplified and got the square root taken, when I use the square root, apply the square root, it has to be 0 or positive. So I have to solve for x. What do I do first? It would be easier just to add the 7x to the other side, but me being the math teacher that I am, I'm going to review a crucial part about inequalities. I'm going to subtract the 5, so I have negative 7x is less than or equal to negative 5. Again, it would be easier just to have added the 7x. And then now I need to divide both sides by a negative 7. And what do you recall about dividing or multiplying both sides of an equation by a negative when dealing with inequalities? The inequality symbol has to switch. Let me highlight this as best I can. That inequality symbol has to flip. It turns around. The reason for this is because the inequalities are inherently unequal. Imagine a seesaw or one of those old traditional scales. They are not equal. So because I could have, let me just go ahead and work this way. I could have out of the 7x, like I said. So 5 is greater than or equal to 7x. Then I could divide both sides by 7, and we'll get 5/7 is greater than or equal to x. If I was to pick this up, imagine I took that inequality, wrote it on plexiglass, picked it up, turned it around. The 7, 5, and 7 would be mirrored, but turned it around. I would then end up with x is flipped around less than, flipped, and then 5/7, which is what this is. Okay, this flips around. When it flips around, so does the inequality symbol. So I could have done this way, which is clearly mathematically correct. And so because of that imbalance, we've created a standard that whenever you divide by the negative, that will then fix that and flip this around for us. Or also just think about this just logically. If I'm multiplying or dividing by a negative, what was positive is now negative. What was negative is now positive. So literally these scales have flipped. So we too need to also flip around the inequality symbol. So x is less than or equal to positive 5/7. So this is in terms of an interval notation. Negative infinity, gross infinities today, negative infinity to 5/7, square bracket. This was we draw a number line right here real fast. Here's 0. Oh look, I found 5/7 is right there. I am on 5/7, but it's less than or equal to, so it goes that way. So I'm going all the way to negative infinity and then journeying up until I touch 5/7. For a set notation, it's the set of x's such that x is less than or equal to 5/7. And there we go. All right. We have two more, but technically one more to do. This one's really important because what do you see? Yeah, is this red alert or business as usual? Well, first I see a denominator, right? So this denominator puts me into red alert. The Klingons are attacking me. Oh, bottle crap. What do we see right here? What's happening underneath that square root? So are the Romulans. We have two different warring factions coming at us at the same time. Oh my goodness, we have to figure out a good plan and deal with this. So let's take care of, I'll do it in blue. Let me do this, just the big one first, that big denominator. So the square root of x plus 2. So the entire denominator. So if I said, what is the denominator? What is the restriction that it has to be? It can't be 0. So whatever is the denominator, set it to be not equal to 0. All right. Oh, I see a square root. Whether the square root was in the denominator or in a numerator, we would set what is under the square root to be greater than or equal to 0. So we do that as well. And let's solve. I'm going to do with the x plus 2 greater than or equal to 0 first, because that's easier. So x has to be greater than or equal to negative 2. And, all right, so let's solve this one on the left. So I have to get that x by itself. So we need that square root to go away. And how do we get rid of square roots? By squaring. So I can square both sides. Literally, if you recall from my exponent review, square root of x, if I have a square root that is literally a 1/2 in a 1/2 exponent. So I'm raising a 1/2 to a second power. The 1/2 in the square, there's the powers multiplied by powers, they reduce to 1. So the square roots and squares reduce each other, and I'm left with x plus 2 does not equal 0 squared. Well, that's just 0. So that means that x does not equal negative 2. Now, both of these things have to agree. Here's the analogy that I use for this to make sense. Imagine that you were to go to an Italian restaurant or a pizza place, one of the fancy pizza places where you can get to pick all your toppings and then they can bring them to you, sit-down restaurant. So they have a list of ingredients. And so you sit down, you look at the menu, you go, oh, I'm good with everything on this menu, but anchovies. I do not want anchovies. Please, for the love, do not put fish on my pizza. All right, and your friend goes, oh, I love anchovies, but I want anchovies, and these items, but oh goodness me, do not put olives and do not put peppers and blah, blah. They start listing off all these things that they're not okay with. They have these others that they're okay with, but they don't like it, but they love anchovies. So what's going to happen? So the analogy here is this is the anchovies. There's just one thing that they're not okay with. No anchovies. This friend is okay with the anchovies, a bunch of other things, but there's a whole like there's like half the list that they're not okay with. If you were to only able to order one pizza and it has to be a pizza that you both agree on, what gets put on the pizza? Well, clearly it's everything that they're okay with eating. But then because you're not okay with the anchovies, the -2, we're going to get rid of that equal sign, right? Think about that, right? So you'd basically be like, okay, fine. We'll get all those things that you want, but you have to take off anchovies or I'm not eating that pizza. And then she goes, okay, fine. So that's how this works. They have to agree, all right? This is where they're intersecting. This mathematically, this actually has to be in an and statement. Okay, they both have to agree. It's where they're sort of kind of intersecting. So let's do our domain. So our domain is from. Let me draw up the number line again. So here's 0. Here's -2. So one person said solid dot greater than. The other person was like, I'm good with everything, just not here. So then where do they agree? Well, they agree with open circle -2 to infinity. All right, so that is from parentheses -2 to infinity, or for the interval notation, sorry, the set notation, the set of x's such that x is greater than -2, but it does not have the equal to part. All right, so that's important about how to be able to smush those together. All right, one last one for this video. We have the cube root of x plus 4. So is this red alert or business as usual? This is business as usual. This is a cube root. Okay? Remember, not everything has restrictions, just square root and rational functions. This is a cube root. So this is fine. This is -infinity to +infinity, all or all real numbers. The set of x's such that x is an element of the real number set. So all real numbers, all of them are fine. This is perfectly fine to do. All right. So hopefully at this point you're good with doing a domain and range of piecewise functions backwards and forwards. And then we understand of our 7 parent functions so far, the rational functions and the square roots have domain restrictions. If you see a rational function, the domain cannot be 0. And then the square root functions, what's under the square root has to be greater than or equal to 0. Just know those 2 facts and then apply them and you'll be good to go. Meet me in the next video where we will be talking about composite functions, which will be using this domain idea as well, because we'll be sticking some functions inside of each other. All right, I'll see you in the next one.